100 billion stars. That is what our galaxy holds. For generations, that number made us feel enormous, special, significant. James Webb just changed that. In a single image, Webb stared into a patch of darkness, smaller than a grain of sand held at arm's length, and found thousands of entire galaxies packed inside it. Each one holding hundreds of billions of stars of their own. Tonight, we travel from our galaxy's edge to the farthest light Webb has ever captured. We will visit galaxies that should not exist, voids so large they break the models, and structures so old they rewrite the origin story of everything. If you enjoy this journey, like and subscribe. It helps more than you know. Now brace yourself. We begin. Stand outside on a clear night and look up. If you are far from city lights, you might see a faint smear of light stretched across the sky. That pale ribbon is our galaxy. Every star you can see with your naked eye belongs to it. For thousands of years, that smear was the entire universe, as far as anyone knew. It felt vast, overwhelming, complete. We now know it is neither complete nor particularly vast. The problem with studying our own galaxy has always been location. We are inside it. Imagine trying to draw a map of a city while standing in the middle of a crowded street, surrounded by buildings in every direction. You can see what is immediately around you, but the full picture stays hidden. That is exactly the challenge astronomers faced for centuries when trying to understand the Milky Way. Ground-based telescopes helped. Then the Hubble Space Telescope pushed further. Scientists mapped large sections of our galaxy using radio waves and infrared light that could cut through clouds of dust. They built models. They calculated the number of spiral arms, estimated the diameter, tracked the motion of stars near the center. The picture improved slowly, piece by piece. By the early 21st century, the scientific consensus was that our galaxy spans roughly 100,000 light-years across. That figure felt enormous. 1 light-year alone is about 6 trillion miles. Multiply that by 100,000, and the number becomes almost meaningless to human intuition. Then James Webb launched. Webb was not designed specifically to study the Milky Way. Its primary mission was to look outward, toward the deepest and oldest regions of the universe. But in doing so, it accidentally reframed everything about how we see our galaxy. Because the moment Webb began returning images of what lies beyond our galaxy, the scale comparison became impossible to ignore. In one confirmed deep field image, Webb captured thousands of galaxies in a region of sky so small it would be covered by a single grain of sand, held out at arm's length. Each of those galaxies contains anywhere from tens of billions to several trillion stars. Some are spiral-shaped like ours. Others are elliptical, irregular, or stretched into shapes we have no simple name for. All of them are complete, independent island universes, and our galaxy is just one among them. The Milky Way is classified as a barred spiral galaxy. It has a central bar structure made of densely packed stars, with several spiral arms curving outward. From above, it would resemble a slow, glowing pinwheel. Scientists are confident about the general shape, though the exact number of arms and their precise layout is still being refined. This is confirmed science, but the fine details remain an active area of research. What Webb made undeniable is that our galaxy, for all its billions of stars, occupies a tiny corner of something almost incomprehensibly larger. The view from inside feels grand. The view from outside tells a very different story. And if that comparison unsettles you even slightly, hold on. Because the next chapter takes us to the specific moment. Webb changed everything. And what it found in a patch of sky that was supposed to be completely empty. In 1995, astronomers pointed the Hubble Space Telescope at a tiny patch of sky near the Big Dipper. The patch was chosen carefully. Scientists specifically selected a region that appeared completely empty. No nearby stars, no known galaxies, nothing visible to any instrument at the time. Colleagues thought the decision was borderline reckless. Why waste precious telescope time staring at nothing? Hubble stared for 10 consecutive days. What came back stunned the entire field of astronomy. That apparently empty patch of sky contained over 3,000 galaxies, each one a fully formed, independent universe of stars. The image became known as the Hubble Deep Field, and it permanently changed humanity's understanding of how filled the cosmos actually is. That was a powerful moment. But Webb went further. When James Webb turned its instruments toward a similar patch of deep sky, it did not just match what Hubble found. It demolished the comparison entirely. Webb's infrared capabilities allowed it to see through dust and across distances that Hubble's visible light detectors could never reach. The result was an image containing thousands of galaxies, some of them so ancient and so far away that their light left before our own planet existed. Think about that for a moment. Light that has been traveling through space longer than Earth has been a planet, and it is just now arriving at Webb's mirrors. The confirmed science here is remarkable. Webb's deep field images show galaxies at distances placing them within the first few 100 million years after the Big Bang. The universe itself is estimated to be around 13.8 billion years old. Some of the galaxies Webb detected formed when the universe was less than 5% of its current age. They were already building stars, already clustering, already evolving on a timeline that surprised many researchers. And all of this happened inside a patch of sky you could cover with a grain of sand. The question that followed was immediate and unsettling. If one tiny sliver of seemingly empty sky contains thousands of ancient galaxies, how many exist across the entire observable universe? Astronomers have now revised that estimate upward dramatically. Earlier models suggested around 200 billion galaxies. After Webb, some researchers believe the true number could be closer to 2 trillion. 2 trillion galaxies, each one a system of stars, planets, gas, and mystery, each one dwarfing anything on Earth in scale. And our galaxy, the Milky Way, is simply one entry in that list. Here is what makes this feel personal rather than abstract. Every photon of light in those Webb images traveled billions of light years before hitting a mirror the size of a dining room table floating silently in space. The telescope did not create that image. It just caught light that had nowhere else to go. The universe was always this full. We just lacked the eyes to see it. But knowing the universe is crowded with galaxies is only the beginning of the story Webb is telling. Because some of those galaxies Webb found should not exist at all. They formed too early, grew too fast, and broke the models astronomers spent decades building. That is where things get genuinely strange. And that is exactly where we are heading next. For most of human history, measuring the cosmos meant measuring what we could see. And what we could see was always limited by our tools, our position, and the physics of visible light. Early astronomers had no way to determine how far away stars truly were. The sky looked flat, a dome studded with lights at unknown distances. Over centuries, better tools arrived. Telescopes improved. Mathematics advanced. Astronomers developed a technique called parallax, which measures the tiny apparent shift in a star's position as Earth moves around our star across the year. It works well for nearby stars, but breaks down at greater distances because the shift becomes too small to detect. For farther objects, Astronomers relied on a class of stars called Cepheid variables. These stars pulse in brightness at a regular rate, and that rate is directly linked to their true luminosity. By comparing how bright they appear to how bright they actually are, scientists can calculate distances. This method pushed measuring tools much further out into the galaxy. It was genuinely revolutionary. But there was a problem baked into all of these methods. They depended on visible light, and visible light cannot travel freely through the Milky Way. The galaxy is filled with clouds of gas and dust, enormous, dense regions that absorb and scatter light before it reaches us. These clouds are not rare. They are woven throughout the spiral arms and concentrated heavily toward the galactic center. The result was a distorted picture. Large portions of our own galaxy were essentially invisible to optical telescopes. Scientists were drawing maps with a significant percentage of the territory permanently blacked out. Estimates of the galaxy's size, its mass, the number of stars it contains, all of these were based on incomplete data. This is confirmed and well documented in the scientific literature. Researchers knew the limitations existed. They built models that accounted for the obscured regions as best they could. But the models were always constrained by what the instruments could actually detect. Radio telescopes helped break through some of that barrier. Radio waves pass through dust clouds more easily than visible light. Infrared light does too, which is exactly why infrared astronomy became increasingly important in the decades before Webb. Spitzer Space Telescope, launched in 2003, was a significant step. It mapped large portions of the Milky Way in infrared and revealed structures, hidden to earlier telescopes. The images were striking, but Spitzer's mirrors were small, and its sensitivity had limits. Then Webb arrived with a mirror over 6 times larger than Spitzer's, operating at temperatures cold enough to detect the faintest infrared signals in the universe. The difference was not incremental. It was transformational. The maps we had of our own galaxy were already being revised before Webb launched. But Webb's ability to pierce through dust clouds and detect incredibly faint and distant sources means the revisions are still ongoing and growing more significant with each new observation cycle. What we are discovering is that the Milky Way is both larger and more complex than previous estimates suggested. New stellar populations are being found. Structures in the outer disk that were invisible before are coming into focus. We thought we knew our home. Turns out we had only seen part of it. And now that the full picture is coming into view, the comparison to everything else Webb is finding becomes even more humbling. Because next, we get to understand exactly how Webb sees what no other telescope could, and what that vision has unlocked in ways no one fully anticipated. Everything we see with our eyes is visible light. It occupies a narrow band of the electromagnetic spectrum, a tiny slice between radio waves on one end and ultraviolet radiation on the other. Human vision evolved to detect this specific range because our star pumps out enormous amounts of it, and the atmosphere allows it through. That is the light we built our first telescopes around. But the universe communicates in far more than visible light. Objects that are very cool, very distant, or buried behind thick clouds of dust emit and absorb light in other parts of the spectrum. Infrared light, which we experience as heat radiation, is one of the most important. It passes through dust clouds that would block visible light entirely. It carries information from the coldest and most distant corners of the cosmos. And critically, it carries the stretched-out signal of ancient light that has been traveling so long, the universe's expansion has shifted it out of the visible range entirely. This last point deserves a pause. When the universe expands, the space between objects stretches. Light traveling through that expanding space gets stretched too. Its wavelength grows longer. Visible light shifts toward red. If it travels far enough, for long enough, it shifts past red entirely and becomes infrared. Astronomers call this redshift. and it is one of the most powerful tools for measuring cosmic distances. To detect the oldest light in the universe, you need an infrared telescope. This is confirmed physics, not a theory. It is the unavoidable consequence of how space and light interact over cosmic timescales. Hubble could detect some infrared wavelengths, but its instruments were limited. More importantly, Hubble operates at near room temperature. Infrared detectors are extremely sensitive to heat. Any warmth in the instrument itself floods the detector with noise, drowning out faint signals from the cosmos. To detect the universe's faintest infrared light, the telescope itself has to be incredibly cold. Webb solved this with engineering that took decades to develop. It operates at roughly negative 448 degrees Fahrenheit, colder than anything found naturally in our solar system. At that temperature, the thermal noise drops to almost nothing. The detectors become exquisitely sensitive. And Webb's primary mirror, made of 18 gold-coated hexagonal segments and spanning over 21 feet across, collects vastly more light than any previous space telescope. The combination produces something extraordinary. Webb does not just see further than Hubble, it sees differently. Where Hubble saw a faint smear of distant light, Webb resolves individual galaxies, their shapes, their star-forming regions, their cores. Plus, where Hubble saw a featureless dust cloud, Webb sees what is happening inside it. New stars being born, jets of material being ejected, planetary systems taking shape. For the Milky Way specifically, this matters enormously. Our galactic center, the dense and chaotic region around the supermassive black hole at the galaxy's core, was previously obscured behind layers of dust so thick that visible light telescopes saw almost nothing. Webb has now produced detailed images of that region. What it found there is still being analyzed. The structures visible in those images were not predicted by earlier models. And that theme of Webb finding things that were not predicted is about to become the central story of this entire journey. Because the oldest galaxies Webb detected do more than impress. They cause serious problems for the leading theory of how the universe formed. That problem starts right now. The Big Bang Theory is the most tested, most supported, and most refined model in all of cosmology. It describes how the universe began from an extraordinarily hot and dense state, roughly 13.8 billion years ago, and expanded outward into the cosmos we observe today. The theory is built on decades of observations, from the cosmic microwave background radiation to the large-scale structure of galaxy clusters to the measured abundance of elements in the early universe. But no theory survives contact with new data unchanged. When Webb turned its mirrors toward the deepest and oldest reaches of the observable universe, it began returning images of galaxies that formed within the first few 100 million years after the Big Bang. This was expected. Astronomers had models predicting what those early galaxies should look like. They should be small, irregular, dim, and still in the early stages of assembling their first stars. The universe had barely begun. There simply had not been enough time for large, complex structures to form. What Webb found did not match those predictions. The images revealed galaxies that were far larger, brighter, and more structurally developed than the models allowed for. Some of these early galaxies contained as many stars as our entire Milky Way and showed signs of organized structure at an age when they should have been little more than chaotic clouds of gas. One confirmed object, placed just over 300 million years after the Big Bang by its redshift measurement, appeared to be a mature, massive galaxy by any reasonable standard. This is confirmed observation. The light is real. The redshift measurements are solid. The question of what these objects mean for our models of galaxy formation is where active scientific debate is happening right now. Several explanations are being explored. One possibility is that the processes driving star formation in the early universe were far more efficient than current models account for. Another is that dark matter, the invisible substance that makes up the majority of matter in the universe, played a more active organizing role early on, pulling gas together faster and creating the conditions for rapid galaxy growth. A third possibility, one that has generated significant discussion, is that aspects of the standard cosmological model itself need revision. This does not mean the Big Bang did not happen. The evidence for that is overwhelming and remains untouched. It means the detailed story of what happened in the first billion years may be more complex and surprising than current models capture. The scientists working on this data are careful and methodical. Extraordinary claims require extraordinary evidence, but the findings are real, and the conversation they are triggering is serious. What makes this directly relevant to our story about the Milky Way's scale is the context it creates. Our galaxy is roughly 10 billion years old. The galaxies Webb is detecting were already forming billions of years before our galaxy existed. They were ancient by the time our own collection of stars began to take shape. Our galaxy is not just small in space. It is relatively young in time compared to the oldest structures the universe has produced. And here is the part that should stay with you. Some of those ancient galaxies that the models said should not exist, they are far larger than the Milky Way. We are only beginning to understand what that means. Something deeper is driving this, and the next chapter follows it directly. Imagine building a skyscraper. The construction follows a sequence. First, the foundation is laid, then the steel frame goes up. Floors are added one by one, walls, wiring, plumbing. It takes years, sometimes a decade or more, and every step depends on the previous one being complete. You cannot install windows on the 50th floor before the 50th floor exists. Galaxy formation was supposed to follow a similar logic. After the Big Bang, the universe was an almost perfectly uniform hot fog of particles. As it cooled and expanded, tiny fluctuations in density caused matter to clump together. These clumps grew slowly under gravity, pulling in gas and dark matter over millions and billions of years. Small structures formed first. Then those structures merged to build larger ones. Galaxies assembled through a long, gradual process of collision, merger, and growth. This model, called hierarchical structure formation, is confirmed by vast amounts of evidence. The cosmic microwave background shows those early density fluctuations. Simulations built on this model successfully reproduce the large-scale structure of the universe as we observe it today. It is one of the most successful frameworks in all of modern astronomy. The problem is the timeline it produces. According to hierarchical formation models, large and structurally complex galaxies should not exist in the very early universe. There was simply not enough time for small structures to merge and grow into massive ones. Building a galaxy the size of the Milky Way through mergers alone takes several billion years. The universe, in its first few 100 million years, should have only produced small, irregular, chaotic proto-galaxies. Webb is finding something different. The rate at which galaxies appear to have formed stellar mass in the earliest cosmic epochs is, in some cases, dramatically higher than simulations predicted. These early galaxies were not just present. They were forming stars at rates that outpace what current models generate for objects at that age and in that cosmic environment. Some galaxies appear to have assembled the equivalent of our entire Milky Way's stellar mass in a fraction of the expected time. Researchers are not dismissing these findings. They are working to understand them. One area of active investigation is the role of the earliest generation of stars, called population 3 stars. These were the first stars to form after the Big Bang, composed almost entirely of hydrogen and helium. They were likely massive, burned intensely, and died quickly in enormous explosions that seeded the surrounding gas with heavier elements. If population 3 stars formed earlier and in greater numbers than models suggest, they could have dramatically accelerated the conditions for galaxy growth. Another angle involves the behavior of dark matter at small scales in the early universe. If dark matter formed denser clumps earlier than expected, it would have provided stronger gravitational scaffolding for gas to collect and form stars at a faster rate. This is currently a theoretical explanation, not a confirmed finding, but it is being taken seriously. What makes this more than an academic puzzle is the scale of the discrepancy. 1 or 2 anomalies might be explained by measurement error or unusual edge cases. A consistent pattern of massive, rapidly formed early galaxies appearing across multiple Webb observations suggests something more fundamental is missing from the model. Something in the story of how the universe built itself is not yet fully understood, and the next chapter puts a specific face to that mystery. Science depends on anomalies. Every major shift in understanding has begun with an observation that did not fit, a measurement that refused to conform, a piece of data that broke the established rules. These anomalies are not embarrassments. They are invitations. They mark the edges of what current theories can explain and point towards something deeper. Webb has delivered several of these anomalies. Astronomers have given them an unofficial but descriptive label. They call them impossible galaxies. The name is not strictly accurate. These galaxies clearly exist. Webb photographed them. Their light has been measured, their distances confirmed, their properties analyzed by multiple independent research teams. Impossible refers not to their existence, but to their relationship with current theory. They exist in ways the standard model of cosmology did not predict and still struggles to explain. One of the most discussed examples is a category of galaxies found at extreme distances, placed by their redshift measurements in the universe's first 500 million years. These objects show stellar masses, the total weight of all their stars combined, that rival or exceed galaxies found billions of years later in cosmic history. They are not slightly above the expected mass range. Some of them are orders of magnitude more massive than simulations predicted for objects at that era. In 2022 and 23, as the first rounds of Webb deep field data came back, several research papers flagged these objects. One widely cited paper stated that these galaxies, if confirmed, would challenge our understanding of early universe physics. Subsequent observations have not resolved the tension. Further study has added more candidate objects to the list. A confirmed finding from Webb is that the universe formed stars in its earliest stages at a higher rate than previously measured. The exact mechanism driving this is still being investigated. Whether it requires modest adjustments to existing models or deeper revisions is a question the scientific community has not yet settled. That distinction matters, and honest reporting requires acknowledging it. What is not in dispute is the size comparison these galaxies force us to make. Some of the oldest detected galaxies, the ones that formed when the universe was still in its infancy, are larger than our Milky Way. They have more stars. They have more mass. They have already lived through phases of evolution that our galaxy is still undergoing, and they did all of this before our galaxy even existed. There is something deeply strange about looking at an image and realizing you are seeing a structure that was already ancient before our entire planetary neighborhood formed. Strange and humbling, in a way that raw numbers alone cannot fully communicate. The impossible galaxies are not just a problem for theorists. They are a mirror. They reflect back a version of cosmic history in which our galaxy arrives late, builds modestly, and occupies no special position in the timeline of structure formation. every explanation being explored for why these galaxies exist: faster star formation, denser dark matter halos, revised models of early physics, each one, if confirmed, will also tell us something new about the constraints that shaped our own galaxy's growth. Our galaxy formed in the conditions those ancient giants helped create. Understanding them is, in a very real sense, understanding ourselves. But the story does not stop at individual galaxies, because these galaxies are not isolated. They exist inside something far larger, and that is where the scale truly becomes overwhelming. Our galaxy is old. There is no question about that. The Milky Way began forming roughly 10 billion years ago, possibly as early as 13 billion years ago for its oldest stellar populations. The oldest stars in our galaxy, found in the halo region surrounding the disk, are estimated to be around 13 billion years old. They formed from the very first generation of enriched material available after the Big Bang. 10 billion years is a number that resists intuition. If you compress the entire history of the universe into a single calendar year, our galaxy would begin forming sometime around late January. Modern humans would not appear until the final seconds of December 31st. Yet even by that scale, our galaxy arrived relatively early. The structure's Webb is now imaging formed before January on that calendar. The most distant, confirmed galaxies Webb has observed existed within the first 2 to 3% of the universe's total lifespan. By the time our Milky Way was beginning to pull together its first stars, some of the galaxies Webb has photographed had already lived through billions of years of evolution. They had formed stars, triggered supernovae, seeded the cosmos with heavy elements, and in some cases, already started to wind down. This is confirmed science. The age estimates of our galaxy's oldest stars come from well-established stellar physics, the rate at which stars of different masses burn through their fuel. The measurements of distant galaxies' ages come from redshift, spectroscopy, and careful analysis of stellar population signals encoded in their light. What Webb has added is resolution. Where earlier telescopes could estimate the ages of distant galaxies only roughly, Webb's sensitivity allows far more precise measurements of stellar populations, chemical compositions, and structural features. The picture of when things formed and in what order is now significantly sharper. Our galaxy has two main components in terms of age. The stellar halo and the thick disk contain the oldest stars, relics from the Milky Way's chaotic early phase, when smaller proto-galactic structures were merging together. The thin disk, where our solar system sits, is younger. Our own star formed roughly 4.6 billion years ago, less than halfway through the current age of the universe. The Milky Way, in other words, is still actively evolving. New stars are being born inside it right now, at a relatively modest rate compared to the galaxy's peak star-forming period billions of years ago, but ongoing. Our galaxy is a work in progress, not an ancient finished structure. Compare that to some of the galaxies Webb has photographed in the distant universe. Large elliptical galaxies, in particular, appear to have formed the majority of their stars extremely early and then gone relatively quiet. They built fast and burned bright. The Milky Way has built more slowly, over a longer time, with a more sustained pace. Whether that slow build approach makes our galaxy unusual or typical is still being determined. Webb is cataloging enough early galaxies now that statistical comparisons are becoming possible for the first time. What is becoming clear is that the universe had a turbulent, creative early phase that produced enormous structures quickly. Our galaxy came of age during the calmer period that followed. That calm, as the next chapter reveals, is relative, because on larger scales, nothing in the universe is ever really sitting still. Our galaxy does not exist in isolation. It belongs to a neighborhood. In astronomy, that neighborhood has a name: the local group. It is a collection of more than 50 galaxies gravitationally bound together, meaning they are close enough and massive enough relative to each other that they will not drift apart as the universe expands. Gravity holds them in a loose, complex dance. The local group spans roughly 10 million light-years across. That sounds enormous, and by any human measure, it is. But in the context of cosmic structure, it is a modest cluster. By galactic standards, our neighborhood is not impressive in scale. The two dominant members of the local group are the Milky Way and the Andromeda Galaxy. These are the two largest galaxies in the group by a significant margin. Most of the other members are smaller satellite galaxies. The large and small Magellanic Clouds are the most well-known neighbors of our own galaxy. Andromeda has its own collection of satellite galaxies as well. Andromeda is similar to our galaxy in general structure, a large barred spiral, but it is notably bigger. Current estimates place Andromeda's stellar mass at roughly 1 trillion solar masses, compared to the Milky Way's estimated range of 700 billion to 1 trillion solar masses. The measurements carry uncertainty, but the comparison suggests Andromeda holds more stars and more total mass. Our nearest large neighbor is, by most measures, slightly more impressive than our own home. This matters because the local group, for all its modest size, is where our immediate cosmic future plays out. Andromeda and the Milky Way are moving toward each other. This is confirmed observational science. The approach has been measured using precise velocity data. In roughly 4.5 billion years, the two galaxies will begin to merge. Webb has been used to study Andromeda in new detail, and what it has revealed about our neighbor adds layers to this already dramatic story. That chapter comes later. What matters here is the context the local group provides. 50-plus galaxies, including two major spirals, held together in a 10 million light-year region of space. To an observer looking at this cluster from a great distance, it would appear as a relatively tight and unremarkable knot of matter, because the local group itself sits inside something far larger. The local group is one small node within the Virgo supercluster, a vast collection of galaxy groups and clusters stretching across roughly 100 million light-years. And the Virgo supercluster is itself just one arm of something larger still. Zoom out far enough and the local group becomes almost invisible, a faint smudge among thousands of similar structures scattered across the observable universe. Webb's deep field images make this vivid in a way that numbers cannot. When you look at those images and count the galaxies, each one a cluster of hundreds of billions of stars, and then remember that each visible galaxy likely belongs to its own group or cluster, the layered nature of cosmic structure starts to sink in. Our 50-galaxy neighborhood feels like home. It is familiar, mapped, and understood. But it is, by the universe's accounting, a footnote. Something far stranger waits just beyond it. The next layer of structure reveals a pattern in the cosmos that no one expected to find, and it raises questions about the universe's architecture that are still not fully answered. In 2014, a team of astronomers published a landmark paper in the journal Nature. Using new methods to map the flow of galaxies through space, they identified a massive superstructure that our galaxy belongs to. They gave it a name from the Hawaiian language, Laniakea. It means immeasurable heaven. The name is fitting. Laniakea is a supercluster of galaxies. It contains the Virgo supercluster, which itself contains our local group, along with hundreds of other galaxy groups and clusters. In total, Laniakea encompasses roughly 100,000 galaxies, spread across a region approximately 500 million light-years in diameter. 500 million light-years. Our galaxy is about 100,000 light-years across. Laniakea is 5,000 times wider than the Milky Way in every direction. And our galaxy occupies a position near the outer edge of it. To understand what Laniakea actually is, it helps to think about how astronomers found it. Galaxies do not move randomly through space. They are drawn toward concentrations of mass, flowing like water toward basins. By mapping the direction and speed of thousands of galaxies' motions, researchers can trace the gravitational landscape underneath. The boundaries of Laniakea are defined not by a visible edge, but by a divide in the flow. Galaxies inside Laniakea are flowing inward toward its center. Galaxies just outside are flowing away toward different attractors. This is confirmed science based on a large catalog of galaxy velocity measurements. The exact boundaries are still being refined as more data comes in, but the overall structure is well established. At the center of Laniakea lies a massive concentration of matter known as the Great Attractor. This region, located roughly 150 million light-years from our galaxy, is pulling everything in Laniakea, including the Milky Way, toward it at hundreds of miles per second. For a long time, scientists could not directly observe the Great Attractor because it lies behind the most dust-obscured region of the Milky Way. Webb's infrared vision has helped begin to penetrate that zone of obscuration. What lies at the center of the Great Attractor region is a dense supercluster of galaxies called the Norma Cluster, along with potentially additional mass concentrations still being mapped. It is a gravitational anchor on a scale that dwarfs anything in our immediate neighborhood. The Milky Way is being moved by Laniakea's gravity right now, every second, every day. We feel no sensation of this motion, but it is real, measured, and confirmed. Our galaxy is not sitting still. It is part of a vast gravitational system, flowing toward a center that itself is moving within an even larger structure. Webb is contributing to this picture by providing better measurements of galaxy distances and velocities at large scales. As more data is processed, the map of cosmic flows is becoming more detailed and more surprising. Our galaxy is not a fixed island in a calm sea. It is a small boat caught in a current we are only now beginning to fully chart. And Laniakea, as enormous as it is itself just a single feature in a larger structure, a network of filaments and voids that forms the backbone of the entire observable universe. That network is the next stop on this journey, and it is unlike anything else in the cosmos. If you could step outside the observable universe and look at it from a distance, what you would see would not be what most people imagine. The universe is not a uniform fog of galaxies scattered randomly in all directions. It has architecture, it has form, a specific, repeating, and deeply strange, large-scale structure that astronomers call the cosmic web. The cosmic web is made of filaments, enormous strands of matter that stretch across hundreds of millions of light-years, connecting galaxy clusters like nodes in a three-dimensional net. Between the filaments lie enormous empty regions called voids. The filaments branch and intersect in a pattern that, when visualized, looks remarkably like neural tissue, like a brain seen under a microscope, or like the root network beneath a forest floor. This resemblance to biological structures has captured public imagination, but it is important to be clear. The similarity is a visual coincidence, not a functional one. The cosmic web is made of galaxies, dark matter, and diffuse gas, connected by gravity over billions of years, not biology. The filaments themselves are not solid structures in any conventional sense. They are vast, elongated overdensities, regions where matter is slightly more concentrated than the surrounding universe. That slight concentration is enough for gravity to trap galaxies, pulling them to flow along the filaments toward the massive clusters at the intersections. The clusters at those intersections can contain hundreds to thousands of galaxies. Our galaxy belongs to one of these filaments. The local group sits near the edge of a filament in a relatively sparse region. The densest parts of the local cosmic web, the massive clusters, are relatively distant from us. We are, in the vocabulary of the cosmic web, a suburban galaxy, not isolated, but not central. This structure was first predicted theoretically and then confirmed observationally. Large galaxy surveys, mapping the three-dimensional positions of millions of galaxies, have produced images of the cosmic web that are striking in their clarity. The filaments are real, measurable, and consistent with predictions from cosmological models. What Webb adds to this picture is depth and detail at the earliest epochs. By identifying galaxies from the first few billion years of cosmic history, Webb allows researchers to trace how the cosmic web formed, where the first filaments appeared, and how the large-scale structure of the universe assembled over time. Early results suggest the web was already beginning to take shape earlier than expected. One of the most visually dramatic Webb findings in this area is the detection of what appears to be a proto-cluster. A group of galaxies in the early universe beginning to cluster together in a region that will eventually become one of the massive nodes in the cosmic web. Seeing this process in action at a time when the universe was a fraction of its current age gives astronomers a direct window into how the skeleton of the cosmos was built. The Milky Way is one small thread woven into one filament of that web. Its position, its neighbors, its future are all shaped by the filamentary structure it sits inside. The cosmic web explains where galaxies are and why they are there. But between the filaments, there is something that challenges those explanations even further. Empty space on a scale that should not be possible. That emptiness has a name, and it is the next destination. Space is not empty. This is one of the most important corrections that modern cosmology has made to our intuitive understanding of the universe. Even in the regions between galaxies, there is diffuse gas, dark matter, stray particles, radiation, and magnetic fields. The interstellar and intergalactic medium is thin to a degree that no vacuum chamber on Earth could replicate. But it is not nothing. Most of space, however, contains very little, and some regions contain almost nothing at all. These are the voids, the vast empty regions between the filaments of the cosmic web. Ordinary voids are common. They fill most of the volume of the observable universe. Galaxies tend to cluster along filaments and at their intersections, leaving the spaces between those structures largely unpopulated. A typical void might span tens of millions of light-years, containing very few galaxies compared to the surrounding filamentary regions. But some voids are on a different scale entirely. They are called supervoids, and they are among the most extreme structures in the observable universe. The most well-studied of these is a structure sometimes called the cold spot supervoid. It sits in the direction of a region in the southern sky associated with an anomalously cold area in the cosmic microwave background radiation. This supervoid is estimated to be roughly 1 billion light-years in diameter. Our galaxy, which spans 100,000 light-years, would fit inside this single supervoid 10,000 times over. Whether this supervoid is the cause of the cold spot in the microwave background is still debated in the scientific literature. One theory suggests that photons of radiation lose energy as they travel through an expanding void, creating a slightly cooler signal. This effect, called the integrated Sachs-Wolf effect, is real and confirmed in principle, but whether it fully explains the cold spot anomaly is not settled. This remains an active area of research. What is confirmed is the structure's existence and its extraordinary scale. Observations from multiple surveys have mapped its boundaries with reasonable confidence. It is real, it is large, and it contains very few galaxies relative to the surrounding universe. 12. 2. 12. It. 12. Webb's contribution to supervoid research is indirect but important. By providing better measurements of galaxy distributions at large scales, Webb helps improve the statistical maps used to identify and characterize voids. As the galaxy catalog built from Webb observations grows, the large-scale structure of the universe, including its void regions, can be mapped in finer detail than before. The existence of supervoids this large creates interesting tensions with standard cosmological models. The models predict that voids should exist, but the largest observed voids push the edges of what the models generate. This is not a crisis for the models, but it is another data point that astronomers are paying careful attention to. To stand hypothetically at the edge of a supervoid and look inward would be to see almost nothing. No galaxies to navigate by, no clusters to anchor the view, just the faint glow of the cosmic microwave background and the imperceptible whisper of dark matter spread too thin to interact with anything. Emptiness on that scale reframes what the universe actually is. Mostly void, occasionally matter, rarely life. And yet the void is not the strangest gravitational feature near our galaxy. Something is pulling on us from a direction we can barely see, and its name alone is enough to make the scale of our existence feel smaller still. Something is pulling on our galaxy. At hundreds of miles per second, the Milky Way, Andromeda, the Local Group, and the entire Laniakea supercluster are flowing toward a region of space in the direction of the constellations Centaurus and Hydra. The source of this pull was identified decades ago through measurements of galaxy velocities. Astronomers gave it a name that captures both its nature and the scale of the mystery: the Great Attractor. The term is not poetic exaggeration. Whatever lies at the Great Attractor's location is massive enough to influence the motion of tens of thousands of galaxies across hundreds of millions of light years. That kind of gravitational influence requires an enormous concentration of mass. Early estimates placed the total mass of the Great Attractor at the equivalent of tens of millions of galaxies like the Milky Way. The problem with studying it is straightforward. The Great Attractor lies almost directly behind the densest part of our galaxy's disk, in a region called the Zone of Avoidance. This is not a name chosen for dramatic effect. It describes a real observational challenge. The dust and gas concentrated along the galactic plane absorb and scatter optical light so effectively that the region behind it was essentially invisible to optical telescopes. Trying to see through the core of our own galaxy to observe something beyond it was, for a long time, simply not possible. Radio telescopes made the first breakthroughs. Radio waves penetrate dust more easily, and surveys using radio observations began to reveal what lay behind the obscuration. The core of what makes the Great Attractor so gravitationally powerful appears to be a massive galaxy cluster called the Norma Cluster, also known by its catalog designation as Abell 3627. It sits roughly 150 million light-years away and contains hundreds of galaxies, packed into a relatively small volume. But the Norma cluster alone does not account for all of the observed pull. A larger structure surrounding it, called the Great Attractor region, seems to involve multiple overlapping mass concentrations. More recently, an even larger structure, called the Shapley supercluster, located further behind the Great Attractor, at roughly 600 million light-years away, has been identified as a possible additional source of the gravitational flow. Whether the Shapley supercluster is the dominant driver of our motion, or whether the Great Attractor region itself is the primary influence, is still being investigated. Both are confirmed to exist. Their relative contributions to our galaxy's motion is an ongoing area of research. Webb enters this picture through its ability to observe infrared wavelengths that cut through the dust of the zone of avoidance more effectively than optical telescopes. While Webb was not specifically designed as a survey telescope for wide-field mapping, targeted observations in the direction of the Great Attractor region have helped refine our understanding of what is hidden there. We are passengers on a galaxy being pulled across the universe by something we cannot directly see from our current position. Our motion is real, measurable, and significant. And yet, no matter how fast we move toward the Great Attractor, the expansion of the universe means we will never actually reach it. The distance is too vast. Space is expanding faster than we can travel across it. We are falling towards something we can never reach, and what Webb has found beyond our galaxy is even stranger. Most people, when they picture a galaxy, picture a spiral, a slowly rotating disk of stars with graceful arms curving outward, a bright, dense center, and a halo of older stars surrounding the whole structure. The Milky Way is a spiral. Andromeda is a spiral. Many of the most photographed galaxies in space are spirals. They have a visual elegance that made them the default mental image of what a galaxy looks like. Webb has complicated that picture significantly. When astronomers look at nearby galaxies, the ones within a few 100 million light-years, spirals are common. Elliptical galaxies, large featureless spheres of old stars, are also common. The universe, in our cosmic neighborhood, has had billions of years to let gravity organize matter into these stable, recognizable shapes. Look back further in time, to the era when the universe was young, and the picture changes dramatically. The galaxies Webb is detecting at extreme distances are often none of these familiar shapes. They are irregular, asymmetric, clumpy, chaotic. Some are long, thin streaks. Some are compact, dense blobs. Some look like they are mid-collision, their structures distorted by gravitational interaction with neighboring galaxies. This is expected to some extent. In the early universe, galaxy formation was a violent and rapid process. Collisions and mergers were far more frequent. The universe was smaller then, meaning galaxies were closer together on average. Encounters that might take billions of years to unfold in the modern universe happened in compressed timescales. Structure had not yet had the time to settle into the smooth, organized forms we see today. What surprised researchers was the degree of diversity and the specific types of structures Webb revealed. Among the confirmed findings, Webb has identified galaxies in the early universe with clumpy, irregular structure on scales that models did not fully predict. The clumps within these galaxies are massive star-forming regions, far larger and more intense than anything in our current galaxy. Some of these single star-forming regions are larger than entire dwarf galaxies today. Webb has also confirmed the existence of compact massive galaxies in the early universe, objects that packed enormous stellar mass into a volume far smaller than modern galaxies of similar mass. How these compact objects evolved into the larger, more spread-out galaxies we see today is an active area of research. What these early galaxies share, regardless of their specific shape, is that they look nothing like the Milky Way. Our galaxy's spiral structure is a product of billions of years of relatively quiet evolution. The orderly winding arms, the settled disk, the gradual pace of star formation, these are features of a mature system that has had time to relax into stability. The galaxy's Webb photographs near the edge of the observable universe were in their chaotic youth. They were building themselves violently and rapidly. They would be almost unrecognizable to anyone expecting the familiar spiral template. And some of them, as noted earlier, grew to sizes that dwarf our galaxy before it even existed. Seeing these early galaxies in detail is like finding photographs of a city from before the roads were laid out, before the grid, before the order, chaotic, energetic, and vastly different from the city standing today. What comes next in this journey is just as surprising, but in a completely different direction, because some galaxies are so diffuse and spread out that they are nearly invisible, and they challenge our definitions in a way no one saw coming. Not all galaxies announce themselves. Some exist at the edge of detection, so faint and spread out that they were only identified relatively recently, and only because astronomers knew to look for them. These are called ultra-diffuse galaxies, and they represent one of the most puzzling categories of structure in modern astronomy. An ultra-diffuse galaxy can span an area as large as the Milky Way, or even larger, yet contain only a fraction of the stars. Where the Milky Way packs hundreds of billions of stars into its disk, an ultra-diffuse galaxy might hold only a few 100 million, spread across the same vast area. The result is a galaxy so faint that early surveys simply missed them. They blended into the background noise of faint light surrounding galaxy clusters. The first systematic discoveries of ultra-diffuse galaxies came from a survey published in 2015, using a telescope in the Canary Islands, specifically designed to detect extremely faint, extended light. The survey identified over 800 ultra-diffuse galaxies in just one galaxy cluster, the Coma cluster. The sheer number implied that these objects were not rare anomalies. They were a common feature of galaxy clusters that had been hiding in plain sight. What makes them scientifically significant, beyond their sheer strangeness, is what they reveal about galaxy formation and dark matter. There are two broad categories of ultra-diffuse galaxy based on their dark matter content, and they are nearly opposite in nature. The first category contains as much dark matter as would be expected for a galaxy of their size, or even more. These galaxies appear to be dark matter dominated. The stars represent only a minor component of their total mass. How galaxies came to contain so much dark matter relative to ordinary matter is not fully understood. One theory is that these galaxies formed in unusually dense dark matter halos early in cosmic history, but failed to attract enough gas to build a normal stellar population. The second category is even stranger. Several ultra-diffuse galaxies have been found to contain almost no dark matter at all. This is a serious problem for models, because dark matter is supposed to be the scaffolding on which galaxies form. Without it, standard theory says a galaxy should not be able to hold itself together long enough to form stars. Yet, these galaxies exist. Webb has been used to study ultra-diffuse galaxies in detail, taking advantage of its sensitivity to detect individual stellar populations within these extremely faint objects. The results are helping researchers understand the age and composition of these galaxies' stars, which in turn provides clues about when and how they formed. The conclusions so far suggest that many ultra-diffuse galaxies formed early and then stopped growing. Something interrupted their evolution. Whether that interruption was environmental, related to gas being stripped away by nearby massive galaxies, or intrinsic to how they formed, remains under investigation. They are quiet, dim, barely there galaxies that nonetheless hold enormous clues about the universe's least understood component. And if ultra-diffuse galaxies represent one extreme, the next chapter presents the complete opposite. A galaxy so enormous that every size comparison we have used so far in this journey suddenly feels inadequate. Wait until you see what the universe is truly capable of building. There is a galaxy in the universe that makes size comparisons feel almost pointless. It sits roughly 1 billion light-years away, anchoring the center of a massive galaxy cluster, and it is by almost any measure the largest known galaxy in the observable universe. Its catalog name is IC 1101. The Milky Way spans roughly 100,000 light-years. IC 1101 spans approximately 6 million light-years in its outer regions. Some estimates push that figure even higher, depending on where the galaxy's faint outer halo is measured to end. Even at the conservative estimate, this galaxy is 60 times wider than ours. Its volume dwarfs the Milky Way by a factor that is difficult to express without the numbers feeling like fiction. They are not fiction. IC1, 10, IC1. One is a confirmed, observed, measured structure. It has been studied by multiple telescopes across multiple wavelengths. Its distance is confirmed by redshift measurements. Its size has been estimated through surface brightness profiles, tracing its light to the outermost detectable extent. What type of galaxy is it? IC 1101 is a supergiant elliptical galaxy. It has no spiral arms, no organized disk structure, no ongoing star formation at a significant rate. It is an ancient, settled structure of old red and yellow stars, the product of billions of years of mergers with smaller galaxies. Over cosmic history, this behemoth grew to its current size by repeatedly absorbing other galaxies through gravitational capture. This process, called cannibalism in some scientific literature, is the mechanism by which the most massive galaxies in the universe accumulate their size. They sit at the center of clusters where gravity funnels smaller galaxies toward them. Over billions of years, those smaller galaxies are disrupted, their stars scattered into the halo, their mass added to the growing giant. IC1 101 has consumed countless galaxies over its history. The faint, extended halo surrounding its core is largely the dispersed remnants of those absorbed structures. Looking at that halo, you are seeing the ghost of hundreds of former galaxies. The Milky Way, in comparison, has had a relatively quiet merger history. It has absorbed smaller dwarf galaxies over its lifetime, but nothing on the scale of what IC 1101 has done. Our galaxy is still a recognizable spiral with intact structure. It has not been cannibalizing its neighborhood the way central cluster galaxies do. There is a reason for this. Location matters enormously in determining a galaxy's fate. Our galaxy sits in a relatively sparse region, near the outer edge of the Laniakea supercluster, in a small group of galaxies. The density of objects around us is low. The mergers we have experienced have been modest. A galaxy like IC 1101, sitting at the gravitational center of a rich cluster, is constantly fed by everything drawn toward it. Webb has observed environments of galaxies similar to IC 1101 at various points in cosmic history, tracing how these massive central galaxies grew and when their growth was most rapid. The findings suggest that much of the mass buildup in these giants happened in the relatively early universe. IC 1101 is what a galaxy becomes when it sits at the center of cosmic structure for billions of years and consumes everything nearby. Our galaxy never had that opportunity. We exist in a quieter, smaller corner of the universe, and that corner is about to get significantly more complicated. There is a collision coming. It has been coming for billions of years, and for the Milky Way, there is no way to avoid it. Andromeda, our nearest large galactic neighbor, is moving toward us. This is confirmed observational science. Astronomers have measured Andromeda's motion toward our galaxy using precise velocity data from multiple instruments over many decades. with measurements refined significantly by the Hubble Space Telescope, and now further detailed by Webb. The closing speed is roughly 68 miles per second. At that rate, the two galaxies will begin their first close approach in roughly 4 to 5 billion years. See, what follows will not be a clean, instantaneous collision. Galaxy mergers are extraordinarily slow by human timescales and chaotic by any standard. When two spiral galaxies of similar size interact, the result is not the orderly merging of two disks. Gravity reaches into each galaxy before the structures even touch, beginning to pull stars off their original orbits. Tidal tails of stars stretch outward across hundreds of thousands of light years. The disk structures are warped and disrupted. Stars that had stable orbits for billions of years are flung onto entirely new paths, some ejected from the resulting system altogether. The process takes billions of years from first close approach to final merger. Computer simulations, using the confirmed mass and velocity data, have produced detailed models of how the collision will unfold. The simulations suggest that after 2 or 3 close passes, the two galaxy cores will eventually settle together and form a new elliptical or lenticular galaxy. Some researchers have given this future galaxy a name in those simulations, Milkomeda. Despite the word collision, the stars within each galaxy are so far apart that actual stellar impacts are almost impossible. The space between individual stars is so vast that two galaxies can pass through each other without any two stars directly colliding. What changes dramatically is the gravitational environment. Orbits are disrupted. Gas clouds are compressed, triggering new waves of star formation. The entire structure of both galaxies is transformed. For our solar system specifically, the probability of being directly disturbed by another star during the merger is extremely low. Our star and the planets around it will most likely survive the event, though the position within the resulting galaxy will be very different from our current location. Webb has added to this picture by providing precise measurements of Andromeda's transverse motion, meaning its movement sideways across the sky, rather than just toward or away from us. Earlier data suggested the collision path was roughly head-on. Webb's observations have helped refine the trajectory, and current models suggest the approach is somewhat more angled, though still clearly on a collision course. The merger will eventually transform two mid-sized spiral galaxies into a single, larger, different kind of structure. Our Milky Way, as it currently exists, is a temporary configuration. It has a lifespan measured in billions of years, and that lifespan will end in a merger. The universe does not preserve things as they are. It builds, disrupts, rebuilds, and builds again on scales. Our minds were never evolved to comprehend, and if the merger of two galaxies is dramatic, what Webb has found lurking at the hidden core of our own galaxy is something that even this collision cannot prepare you for. For as long as astronomers have studied the Milky Way, there has been a blind spot, not a metaphorical one. A literal, physical region of the sky where dust and gas are so thick that optical light cannot pass through. This region runs along the plane of our galaxy, the dense equatorial band where the disk concentrates its matter most heavily. Astronomers gave it a name: the zone of avoidance. The name captures both the observational challenge and, historically, the practical response. Early sky surveys simply skipped it. What could not be seen could not be catalogued. The assumption, reasonable at the time, was that whatever lay behind the galactic plane was probably not radically different from what was visible elsewhere in the sky. That assumption turned out to be wrong in ways that matter significantly. Radio surveys in the latter half of the 20th century began to peer through the obscuration using wavelengths that dust cannot block. What emerged from those surveys was the first evidence that significant structures, including massive galaxy clusters, were hidden directly behind the plane of our own galaxy. The zone of avoidance was not empty. It was obscured. Infrared observations pushed further. Dedicated surveys using infrared wavelengths identified thousands of galaxies hidden behind the galactic plane that had never appeared in any optical catalog. The Norma cluster, closely connected to the Great Attractor discussed earlier, was among the most significant findings from those surveys. A massive concentration of galaxies had been sitting behind our galaxy's disk this entire time, invisible to the tools astronomers had relied on for generations. Webb takes this further than any previous instrument. Webb's infrared sensitivity is dramatically greater than earlier infrared space telescopes. Its ability to resolve individual structures within distant and dust-obscured regions provides a level of detail that earlier surveys could not achieve. Targeted observations in the direction of the zone of avoidance have begun to reveal individual galaxies, their morphologies, and in some cases, their stellar populations, at distances and with clarity that was simply not possible before. Among the confirmed findings from these observations, previously uncatalogued galaxies have been identified within the zone of avoidance that add to the mass estimates of the Great Attractor region. The overall gravitational environment pulling on our galaxy and its neighbors is being revised upward as more hidden mass is uncovered. There is something philosophically striking about this discovery. Our understanding of the large-scale structure of the universe, the cosmic web, the Great Attractor, the direction and speed of our galaxy's motion, all of it has been built with a significant portion of the nearby sky simply missing from the data. Conclusions drawn from incomplete maps. Webb is filling in some of those gaps, and with each new image of a previously hidden galaxy, the map becomes more accurate and the picture it paints becomes more complex. There is also something unsettling in the implication. If structures of significant mass were hiding directly behind our own galaxy all along, what might be hiding in other regions of the sky that are obscured for different reasons? What lies in directions we have not yet looked with sufficient depth or sensitivity? The zone of avoidance was the most obvious blind spot, but the universe is large enough to hold surprises in every direction. And one of those surprises involves not what is hidden by dust, but what is hidden by something far more absolute. A boundary that no telescope, no matter how powerful, can ever cross. That boundary has a name, and what lies beyond it is, in the most literal sense, forever. Draw a circle around yourself. Now imagine that circle represents the furthest point from which light could ever reach you, not because anything blocks it, but because the universe itself has a speed limit and a finite age. Everything inside that circle is the observable universe. Everything outside it is real, but permanently beyond your reach. This boundary is called the cosmic horizon. It is one of the most profound concepts in all of modern cosmology, and it has nothing to do with what telescopes can or cannot detect. It is a fundamental feature of how the universe works. The universe is approximately 13.8 billion years old. Light travels at a fixed speed. Therefore, the furthest light that could possibly reach us is light that left its source roughly 13.8 billion years ago. Simple logic suggests that the observable universe should therefore have a radius of about 13.8 billion light-years, but it does not. The actual radius of the observable universe is closer to 46 billion light-years in every direction. The reason is cosmic expansion. While light has been traveling toward us, the space it was traveling through has been expanding. The regions of space that emitted the oldest light we can detect have, in the time it took that light to reach us, moved much further away. We see those regions as they were billions of years ago, but they now exist far beyond the distance their ancient light implies. This is confirmed physics, derived from the measured expansion rate of the universe, combined with the known age of the cosmos. it is not a theoretical guess. It is a geometric consequence of how space, time, and light interact in an expanding universe. Webb operates within this boundary. Every image it captures, every galaxy it detects, every spectrum it measures comes from inside the observable universe. That is the only universe accessible to any instrument humanity could ever build, not because of technological limits, but because of physics. What lies beyond the cosmic horizon? Honest science can only say, more universe, most likely structured similarly to what we observe, but forever inaccessible. Whether the universe extends infinitely beyond the horizon, or whether it eventually curves back on itself, or whether it has a finite size that we could in principle measure if physics allowed us to look beyond the horizon, these are questions that current science cannot answer from within the boundary. What Webb has contributed to our understanding of the cosmic horizon is a sharpened picture of what is near it. The most distant, confirmed galaxy detections from Webb are placed within the first few 100 million years of cosmic history, representing light from near the beginning of galaxy formation. These objects sit close to the practical limit of what any optical or infrared telescope can detect, because before a certain point in cosmic history, the universe had not yet become transparent to light. The earliest light that can travel freely through the universe is the cosmic microwave background, a faint glow of radiation that fills the sky in every direction and dates from roughly 380,000 years after the Big Bang. Before that, the universe was a dense, opaque fog that light could not escape. That fog marks the practical edge of what Webb, or any future telescope, can image directly. We live inside a sphere of information. Everything outside it is silence. And yet, even within that sphere, something deeply strange is happening to the galaxies near its edge. They are not simply far away. Some of them are unreachable in a way that goes beyond distance. Distance is a concept humans understand intuitively. Something far away is difficult to reach. Something very far away takes longer. But given enough time, enough energy, enough technology, far away is still, in principle, reachable. The universe does not obey that intuition. The universe is expanding. Space itself is stretching, and that expansion is not happening at a fixed, slow rate. Due to a force called dark energy, the expansion is accelerating. Every second, the space between galaxy clusters grows slightly faster than the second before. The universe is not just big, it is becoming effectively bigger at a rate that is increasing. This creates a category of object unlike anything in ordinary human experience. Galaxies that are currently visible to us, that we can photograph and study, but that we could never reach no matter how fast we traveled. Not because they are too far in any conventional sense, but because space between us and them is expanding faster than any physical object could ever move. This boundary is different from the cosmic horizon discussed in the previous chapter. It is called the Hubble sphere, sometimes called the Hubble volume. Objects beyond a certain distance are receding from us faster than the speed of light, not because they are moving through space at that speed, which would violate the rules of physics, but because the space between us is expanding. The light from those galaxies can still reach us, traveling toward us through expanding space, but we could never travel to them. The confirmed science here is this: there are galaxies in the observable universe that we can see but could never visit. Their light reaches us, but our matter could never reach them. They exist in a region of space that is, for any physical traveler, permanently inaccessible, regardless of technology. Webb has photographed many of these galaxies. Some of the ancient, chaotic structures near the edges of Webb's detection limit fall into this category. We are receiving their light now. That light carries information about what those regions of space looked like billions of years ago. But those regions, in their current state, are beyond any conceivable physical reach. There is something deeply strange about this. We can build a photograph of something we can never touch. We can measure the chemical composition of a star that no human, no probe, no signal we ever send could reach. The universe allows us to know things we can never interact with. The acceleration of cosmic expansion means this situation is getting worse over time. Galaxies that are currently on the edge of reachability are being pushed further past that edge every moment. Future observers, billions of years from now, will see fewer galaxies because more of them will have crossed beyond the horizon, where their light can no longer reach us. The universe visible to our distant descendants will be smaller than the one visible to us today. Webb is, in a sense, capturing images of things that future observers will never be able to see at all. The ancient galaxies. Webb photographs are receding. Their light arriving now is the last light from those specific epochs that will ever complete the journey. This is not a concern for practical astronomy today, but it places our current moment in an interesting context. We exist at a time when the observable universe is still filled with evidence of its own history. Every image Webb captures is a record of something that may, in the very long run, become invisible. The universe is generous with knowledge in the short term. What dark energy is doing to that generosity over cosmic time is another matter entirely. And dark energy's companion, dark matter, is the next piece of this story. Most of the universe cannot be seen. This statement sounds like hyperbole. It is not. Everything visible in a Webb image, every galaxy, every star, every glowing cloud of gas, represents a small fraction of the total matter in the universe. Current estimates, built from decades of observation and refined cosmological modeling, suggest that ordinary matter makes up roughly 5% of the total energy content of the universe. Dark energy makes up about 68%. The remaining 27% is dark matter. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way that current instruments can detect. Its existence is inferred entirely from its gravitational effects, and those effects are enormous. And the evidence for dark matter is extensive and comes from multiple independent sources. Galaxies rotate in ways that cannot be explained by the gravitational pull of their visible stars alone. The outer stars of spiral galaxies orbit at nearly the same speed as the inner stars, which should not happen if gravity came only from visible mass. The mathematics requires additional mass that is not visible. This discrepancy was first systematically documented by astronomer Vera Rubin in the 1970s and has been confirmed repeatedly since. Galaxy clusters bend light more than their visible mass accounts for. This phenomenon, called gravitational lensing, occurs because mass curves space, and curved space deflects the path of light traveling through it. When astronomers measure how much a cluster bends the light of galaxies behind it, they consistently find that the visible mass falls far short of explaining the degree of bending. Something invisible is contributing additional gravity. That something is dark matter. The cosmic web itself, the large-scale filamentary structure connecting galaxy clusters, could not exist in its current form without dark matter. The slight density fluctuations in the early universe would not have had enough gravitational pull to collapse into the structures we see today if only ordinary matter were involved. Dark matter amplified those fluctuations, providing the gravitational scaffolding on which all visible structure was built. Webb contributes to dark matter research primarily through gravitational lensing studies. By precisely measuring how galaxy clusters bend and distort the light of galaxies behind them, Webb's sensitivity allows more detailed mapping of where mass is concentrated in clusters, including the dark matter component. These maps are producing results with finer resolution than previously possible. One specific area of active investigation is the distribution of dark matter at the centers of galaxy clusters. Models predict a dense concentration of dark matter at the core, called a cusp. Observations have sometimes suggested a flatter central distribution, called a core. This discrepancy between predictions and observations, known as the cusp-core problem, is one of the open questions that Webb data is helping to address. What this means for the Milky Way is direct and concrete. Our galaxy exists inside a dark matter halo, an extended, roughly spherical region of dark matter that surrounds the visible disk. The halo is estimated to be significantly larger than the visible galaxy, perhaps extending out to several 100,000 light-years in every direction. The dark matter halo provides much of the total gravitational mass that holds the disk together and keeps the satellite galaxies of the Milky Way in their orbits. Our galaxy is, in a very real sense, a small visible island inside a much larger invisible structure. The dark matter halo is the true extent of the Milky Way's gravitational domain, and the full map of that domain is only beginning to come into view. What it reveals about our galaxy's place in the cosmos is more unusual than most people realize. Counting galaxies should be straightforward in principle. Look at a region of sky, count the galaxies you see, calculate how that region relates to the total sky, and multiply. The answer you get is an estimate of the total number of galaxies in the observable universe. For decades, that estimate hovered around 200 billion. The Hubble Deep Field images, which first revealed the extraordinary density of galaxies in seemingly empty patches of sky, formed the basis for that number. 200 billion galaxies, a figure so large it stopped being intuitive and became simply a very big number. Webb has complicated that figure. The issue is not just counting what is visible, it is accounting for what is too faint, too small, or too distant to detect even with current instruments. Galaxies exist across a wide range of sizes and brightnesses. The most massive, brightest galaxies are easy to detect even at great distances. But galaxies at the small, faint end of the distribution are far harder to identify. Many may exist below the detection threshold of even Webb. A 2016 study by Christopher Consellis and colleagues, using deep Hubble data combined with theoretical modeling, proposed that the true number of galaxies in the observable universe might be closer to 2 trillion, roughly 10 times higher than the earlier estimate. The vast majority of these would be small, low-luminosity galaxies that telescopes have not yet been able to individually detect. This figure is still considered theoretical, not a directly confirmed count. It is based on extrapolating the observed population to account for galaxies below detection limits. What Webb is doing is pushing those detection limits downward, beginning to directly image fainter and more distant galaxies that earlier surveys could only estimate. As Webb's data accumulates, the statistics of galaxy populations are being revised. Early results confirm that small, faint galaxies were significantly more abundant in the early universe than was previously measured. The number density of galaxies at high redshift is higher than models predicted. Whether this eventually pushes the total galaxy count toward 2 trillion or settles somewhere different is still being worked out. What the number means for our galaxy is a matter of context rather than calculation. The Milky Way is one among many. Among a staggering number of other complete star systems, each one containing billions of suns, each one potentially harboring worlds, each one with its own history of formation, evolution, and eventual fate. There is a version of this information that can feel overwhelming to the point of meaninglessness. If the number of galaxies is incomprehensibly large, does any single one matter? The scientific answer to that question is precise. Every single galaxy contributes to the statistical understanding of how structure forms and evolves in the universe. Each one is a data point in the story of cosmic history. The human answer is different and perhaps more interesting. Out of 2 trillion possible galaxies, ours is the only one we know for certain, contains observers capable of asking the question. That may be a result of our limited knowledge rather than a fact about the universe, but it remains true for now. 2 trillion galaxies, one confirmed to hold life. The ratio, whatever it ultimately means, is worth sitting with for a moment. But before moving forward, there is a question about our galaxy's neighborhood that deserves a direct answer. Our cluster of galaxies is unusually small by cosmic standards. Understanding why tells us something important about the conditions that made our galaxy what it is. The Milky Way belongs to the local group, a collection of more than 50 galaxies spread across roughly 10 million light-years. By human standards, any collection containing 50 galaxies sounds enormous. By the universe's standards, the local group is modest in almost every way. Understanding why our cluster is small and what that means for the galaxy that formed inside it reveals something important about how environment shapes cosmic evolution. Galaxy clusters exist across a wide range of sizes and masses. At the extreme end are rich clusters containing hundreds to thousands of large galaxies, surrounded by thousands more smaller dwarf galaxies, all embedded in vast halos of hot gas and dark matter. The Coma cluster and the Virgo cluster are nearby examples of this type. These rich clusters represent regions of space where matter was particularly concentrated when the universe was young, giving gravity a strong early advantage in pulling material together. The local group is not that. It is what astronomers classify as a poor group. The total number of large galaxies is 2, the Milky Way and Andromeda. The rest are satellite galaxies and dwarf galaxies of varying sizes. The total mass of the group, including dark matter, is estimated at several trillion solar masses, respectable by any absolute measure, but far below the mass of rich clusters that can exceed 1,000 trillion solar masses. Why did our region of space produce a poor group rather than a rich cluster? The answer lies in the initial conditions of that region of the universe. Some parts of the early universe had slightly higher density fluctuations, meaning matter was more concentrated there. Those regions attracted more material, triggered faster collapse, and grew into rich clusters. Other regions had lower initial densities. They produced smaller, sparser groups. Our region of space happened to fall into the lower density category. The conditions that led to the local group were established within the first fraction of a second after the Big Bang, encoded in tiny variations in the distribution of matter at the very beginning. This is confirmed science, supported by both observations of the large-scale structure of the universe and by cosmological simulations that reproduce the distribution of cluster masses we observe. What this means practically is that the Milky Way formed in a quieter, less crowded environment than galaxies in rich clusters. It experienced fewer major mergers. It was not repeatedly disrupted by close gravitational encounters with other large galaxies. It was not immersed in hot cluster gas that can strip away a galaxy's own gas supply and shut down star formation. Galaxies in the cores of rich clusters tend to be elliptical, old, and no longer forming stars. Their gas was consumed or removed long ago. Our galaxy, by contrast, is still a spiral. It is still forming new stars. It still has a supply of gas in its disk. The spiral structure of the Milky Way, its ongoing star formation, its relatively ordered disk, all of these features are partly a product of where we formed. Had our galaxy been born in the center of a rich cluster, it would likely look very different today. Older, more settled, no longer building. Our galaxy's characteristics are shaped by its address in the universe. And that address, it turns out, is about to change in ways that will reshape the galaxy entirely. But first, there is a discovery Webb made about the timing of galaxy formation that puts everything into a new perspective. Because something happened far earlier in cosmic history than anyone expected, and its implications are still being sorted through. Science builds timelines carefully. In cosmology, the timeline of the universe is constructed from multiple independent lines of evidence. The measured expansion rate of the universe, the temperature and pattern of the cosmic microwave background, the ages of the oldest stars, the observed distribution of galaxies at different distances. These lines of evidence, coming from entirely different kinds of measurements, converge on the same picture. The universe is approximately 13.8 billion years old. Galaxy formation began within the first few 100 million years. Large, mature galaxies took billions of years to assemble. This timeline is not a loose estimate. It is a precisely constrained framework built from extensive, carefully verified data. It is one of the most successful achievements in the history of science. Webb is stressing it, not demolishing it, not disproving it, but finding objects at the edges of the observable universe whose existence pushes the boundaries of what the timeline permits, and doing so consistently enough that the scientific community is taking it seriously as something more than statistical noise. The specific tension is this: the standard timeline predicts that the earliest galaxies should be small, irregular, and in the early stages of forming their first stars. The mass of a galaxy like the Milky Way should take billions of years to accumulate through the slow gravitational process of hierarchical assembly. Webb has found objects at extreme distances, confirmed by redshift to exist within the first few 100 million years of cosmic history, that appear to already contain stellar masses comparable to or exceeding the Milky Way. One paper published in 2023, analyzing a sample of candidate massive early galaxies from Webb data, described them as potential challenges to the standard cosmological model. The researchers were careful in their language. The measurements carry uncertainties. Some objects may be at slightly lower redshifts than their initial estimates suggested. Not every candidate in the sample may survive further analysis, but enough of them appear robust to keep the conversation open. The question being asked is, did the early universe have a mechanism for building galaxy mass faster than the current models allow? Several possibilities exist. One is that the first stars, the population 3 stars mentioned earlier, were more numerous and formed earlier than current models generate. Their rapid deaths in supernova explosions could have seeded surrounding gas with the heavier elements needed to cool rapidly and form stars at an accelerated pace. Another possibility is that feedback processes, the ways in which star formation and black hole activity regulate themselves in galaxies, worked differently in the early universe's denser, more energetic environment. A third and more provocative possibility is that the parameters describing dark matter's behavior in the early universe need revision. If dark matter formed clumps more efficiently than current models generate, the gravitational scaffolding for rapid galaxy formation would have been in place earlier. None of these explanations have been confirmed. All of them are being actively researched. The honest scientific position is that Webb has found something that the current models did not predict, and the community is working to understand whether the solution is a modest calibration or something more fundamental. What is not in question is the implication for the Milky Way's place in the timeline. Our galaxy formed billions of years after some of these objects existed. We arrived in a universe that was already populated with ancient, massive structures. Our galaxy is not among the oldest. It is not among the most massive. It formed in an already aging cosmos. And what happens to galaxies as they age? The full arc of birth and death is the next chapter of this story. Everything in the universe has a lifespan. Stars are born, burn through their fuel, and end in ways determined by their mass, either as quiet white dwarfs, neutron stars, or spectacular black holes. Planets form, cool, and eventually freeze or burn depending on their star's fate. And galaxies, those vast collections of hundreds of billions of stars, also have a life cycle. They are born, they grow, they change, and in a meaningful sense, they die. Galaxy death is not an explosion or a dramatic single event. It is quieter and stranger than that. Astronomers call it quenching. A galaxy dies when it stops forming new stars. Active, star-forming galaxies are blue and bright. Their disks are populated with young, hot, massive stars that burn intensely and die relatively quickly, but whose formation keeps the galaxy's population young and luminous. When star formation stops, the massive young stars die off. What remains are older, cooler, redder stars. The galaxy fades from blue to red. Its light dims. It settles into a passive state where it continues to shine, but with a diminishing cast of aging stars and no new ones to replace them. The Milky Way is still forming stars, though at a rate lower than its peak several billion years ago. It is a living, active galaxy by this measure, but it will not remain so forever. Several mechanisms can quench a galaxy. One of the most powerful involves the supermassive black hole at a galaxy's center. When large amounts of gas fall into the central black hole, it becomes what astronomers call an active galactic nucleus. The energy released by this process is extraordinary, generating jets of radiation and matter that can travel across the entire galaxy, heating the surrounding gas and preventing it from cooling enough to collapse into new stars. This feedback mechanism can effectively shut down star formation across an entire galaxy. Webb has observed active galactic nuclei at extreme distances, in some cases detected in galaxies from the first billion years of cosmic history. The finding that supermassive black holes were already active and feeding at such early times was not fully anticipated by models. How these black holes grew so large so quickly in galaxies that had only recently begun forming stars is one of the most active areas of Webb-driven research. Environmental quenching is another mechanism. Galaxies falling into rich clusters can have their gas supply stripped away by the hot diffuse gas that fills the cluster environment. As the galaxy moves through this hot medium, ram pressure strips its own gas outward, like wind stripping water from a moving car. Without gas, the galaxy cannot form new stars and gradually reddens and fades. Because the Milky Way is not in a rich cluster environment, this type of quenching is not currently relevant to us. But the eventual merger with Andromeda will change our environment significantly. The resulting combined galaxy, Milkomeda, will likely be an elliptical or lenticular structure with a changed star formation history. Webb has captured images of galaxies at various stages of this life cycle, from violently star-forming systems in the early universe to passive red ellipticals that have been quiet for billions of years. The data is building a statistical picture of how galaxies transition through these phases and what determines the timing. Looking at those images, the Milky Way, in its current spiral, star-forming state, looks young compared to the ancient, settled systems Webb has catalogued. We are in the active phase of a life cycle that, over cosmic time, ends in a quiet, red fade. But the last light a galaxy ever emits is not the end of what it leaves behind. And how we look at time itself, through a telescope, changes everything we thought we knew about sequence and history. Every telescope is a time machine. This is not a metaphor. It is a direct consequence of how light and distance work together in a universe where nothing travels faster than light. When you look at something 1 light year away, you are seeing it as it was 1 year ago. The light entering your eyes or your telescope's mirror left its source 1 year before it arrived. At 1 light year, this is a minor consideration. At cosmic distances, it becomes transformative. The nearest large galaxy to our own, Andromeda, sits roughly 2.5 million light-years away. When Webb observes Andromeda, the light it collects left that galaxy 2.5 million years ago. We are seeing Andromeda as it existed before our species walked on Earth. Push further out, and the temporal gap grows proportionally. Galaxies observed at distances of 1 billion light-years are seen as they were 1 billion years ago, when Earth existed but complex animal life had not yet appeared. Galaxies at 10 billion light-years are visible as they existed before our solar system formed. At the furthest distances Webb can observe, we are seeing the universe as it was when it was less than 1 billion years old. This is confirmed physics, a direct result of the finite speed of light. It requires no exotic assumptions. It follows inevitably from the measured speed of light combined with the measured distances to galaxies. What makes this scientifically powerful is that it allows cosmologists to study the universe at different epochs without theoretical extrapolation. The history of cosmic evolution is written across the sky. Looking outward in space is the same as looking backward in time. A survey of galaxies at different distances is, simultaneously, a survey of galaxies at different stages of evolution. Webb exploits this ability more powerfully than any instrument before it. Its sensitivity allows it to detect galaxies at extreme distances, corresponding to extreme look-back times, with sufficient resolution to study their detailed properties. Earlier telescopes could reach those distances, but could not resolve the structures well enough for detailed analysis. Webb can see individual star-forming regions within galaxies that existed when the universe was a fraction of its current age. This is why Webb's discovery of unexpectedly massive and developed early galaxies carries so much weight. Those observations are not based on models or simulations. They are direct images of the universe at earlier times. The evidence is written in the light. For the Milky Way, this perspective provides important context. When we look at the galaxy's Webb photographs near the edge of the observable universe, we are looking at galaxies that, today, in real present-day time, could be entirely different structures. They have had billions of years to evolve since that ancient light left them. The chaotic early galaxy Webb captured may now be a quiet elliptical. The protocluster Webb detected may now be a rich, massive cluster. We see the past. We cannot see the present state of those distant objects. The universe's true current configuration is hidden from us by the finite speed of light. There is something deeply isolating about this. Every other galaxy, everything Webb photographs, exists in a version of the present that we cannot access. We receive only ancient messages from across the cosmos. And if we cannot see the current state of distant galaxies, the reverse is equally true. Whatever distant civilization might exist in those far-off galaxies would see the Milky Way as it was billions of years ago. What would they see? That question leads somewhere unexpected. Imagine an astronomer on a planet in one of the galaxies near the edge of Webb's detection range. The distances involved place that hypothetical observer roughly 10 billion light-years from the Milky Way. If that observer, equipped with a telescope vastly more powerful than any we have built, pointed their instrument in our direction, what would they see? Not what we see when we look at our galaxy today. Light leaving the Milky Way right now will not reach that distant observer for 10 billion years. What arrives at their telescope today is light that left our galaxy 10 billion years ago. At that time, the Milky Way was roughly 3 to 4 billion years old. Our solar system did not yet exist. Earth did not exist. The galaxy was in a far more active phase of star formation, building stars at a rate several times higher than today. Those distant observers would see a younger, bluer, more actively star-forming version of the Milky Way. The spiral structure may have looked different. The disk was still assembling, still being shaped by the mergers and accretion events of the galaxy's early history. The supermassive black hole at the center was almost certainly more active, feeding on more available gas and producing energetic outflows that shaped the surrounding region. In practical terms, the Milky Way 10 billion years ago would look broadly similar to some of the star-forming spiral galaxies we observe at intermediate distances with Webb today. Active, bright, in ultraviolet light, with regions of intense star formation scattered throughout the disk. This thought experiment does something useful for our understanding of cosmic scale. It reframes the Milky Way not as a fixed, permanent structure, but as a stage in an ongoing process. What we call the Milky Way today is a snapshot. From a cosmological perspective, our galaxy is always in transition, always becoming something different. It also highlights the mutual isolation of different regions of the universe. We see distant galaxies as they were. They see us as we were. The present tense universe, the actual current state of everything simultaneously, is unknowable to any single observer. There is a technical term for the set of events that a given observer can currently influence: the causal horizon. Everything within our causal horizon is something we could, in principle, send a signal to or receive a signal from at some point in our future. Everything beyond it is permanently isolated in terms of cause and effect. The Milky Way sits inside its own causal horizon, able to interact with nearby galaxies, within the cosmic neighborhood, but increasingly isolated from the most distant structures as the universe expands and the causal horizon shrinks over cosmic time. In a very long run, the Milky Way, or whatever structure it eventually becomes after its merger with Andromeda, will be even more isolated than it is today. The accelerating expansion of the universe will push other galaxy groups beyond the causal horizon one by one. The local group will eventually be the only gravitationally bound structure visible to our descendants, marooned in a universe that has expanded all other galaxies beyond sight. If civilizations exist elsewhere and are watching the Milky Way from great distances, they are seeing a galaxy that no longer exists in its current form. We are a historical image on their screens, and we are doing the same to them. Looking out with Webb, we are seeing versions of the universe that are ancient history. The question of what Webb's findings mean for the big picture, for the entire framework of cosmology, deserves a full reckoning now. The Big Bang Theory is not a theory about an explosion. It is a theory about the origin and evolution of space, time, and all matter and energy. It describes how the universe began in an extraordinarily hot, dense state, and has been expanding and cooling ever since. It is supported by multiple independent lines of evidence that converge on the same conclusion with remarkable precision. None of that is changing. What Webb is doing is not overturning the Big Bang. It is stressing the detailed models built on top of it, the specific predictions about how fast galaxies formed, how massive they could be at early times, how the universe's large-scale structure assembled. These models, grouped under what is called the lambda cold dark matter framework, are the current standard cosmological model. They have been extraordinarily successful at explaining a wide range of observations. But no model survives confrontation with new data unchanged. The tension Webb has introduced is real and is being taken seriously by the cosmological community. Papers acknowledging the discrepancy between Webb's early galaxy findings and lambda cold dark matter predictions have appeared in major journals. Researchers are exploring whether the solution lies within the model's existing parameter space, requiring only modest adjustments to assumptions about star formation efficiency or dark matter behavior, or whether something more fundamental is being revealed. One modification being explored is a revised treatment of how the first stars formed and how quickly they could have seeded the early universe with the heavier elements needed for efficient galaxy building. Another involves questioning whether dark matter behaves at small scales exactly as the simplest models assume. Alternative dark matter models, such as warm dark matter or fuzzy dark matter, predict somewhat different behavior at the small scales relevant to early galaxy formation. A more radical suggestion proposed by some researchers is that aspects of the cosmic expansion history itself may need revision. A precise measurement called the Hubble constant, which describes the current rate of the universe's expansion, has shown a persistent discrepancy between measurements made using the early universe as a reference and measurements made using nearby objects. This discrepancy, called the Hubble tension, has been discussed in cosmology for years and remains unresolved. If the expansion history of the universe is slightly different from what standard models assume, it would affect predictions about the timing and rate of structure formation. Webb is actively contributing data to the Hubble tension problem as well. Its precise measurements of Cepheid variable stars in nearby galaxies, which are used to anchor one of the measurement chains, have refined earlier results. As of the current literature, the tension has not been resolved. It remains one of the significant open questions in cosmology. The honest summary of where things stand is this: Webb has found things that the current models did not fully predict. The scientific community is actively working to understand what this means. Some of the discrepancies may be resolved with modest model adjustments. Some may require more significant revisions. The possibility that something genuinely new about the universe's early history is being revealed is taken seriously, but has not been confirmed. This is science working exactly as it should. Not a crisis, not a revolution declared prematurely. A genuine, ongoing confrontation between new data and existing theory. What comes out of that confrontation will shape cosmology for the next generation. And whatever it produces, the central message that Webb's observations keep returning to, the story of how small our galaxy truly is, remains undimmed. One more reckoning awaits, the final one, and it puts everything in its place. Step back, as far back as the observable universe allows. Imagine the entire cosmos laid out as a map, a three-dimensional structure of extraordinary complexity spanning 46 billion light-years in every direction from where we stand. The map would show the cosmic web in its full form. Filaments of galaxy clusters stretching like threads, voids of near emptiness occupying the vast spaces between them, nodes of intense density where the most massive clusters anchor the web at its intersections. Zoom in by a factor of thousands, and a single supercluster appears. Laniakea. 500 million light-years across, containing hundreds of galaxy groups and clusters, flowing toward the dense mass of the Great Attractor at its core. Inside Laniakea, one modest cluster, the Virgo supercluster. Zoom in further. The Virgo supercluster resolves into its constituent groups. One of them, near the outer edge, small and sparse against the broader cluster, the local group. Inside the local group, two dominant galaxies, Andromeda, slightly larger, and ours, the Milky Way. This is the confirmed map that modern astronomy has assembled. Every layer of it is supported by observation, measurement, and evidence. Webb, has not invented this map. It has sharpened it, filled in missing details, extended it closer to the beginning of time than any previous instrument, and made the comparisons at every scale more vivid. What Webb has added is the temporal dimension. The map is not just a snapshot of now, it is a history of how this structure assembled, layer by layer, over 13.5 billion years. The ancient, massive galaxies detected at extreme distances are the earliest nodes of a web that was already forming while the universe was in its infancy. Our galaxy came later, forming in conditions shaped by everything that came before it. We are newcomers in an old universe, late arrivals to a map that was already being drawn when Earth's star had not yet ignited. This perspective can feel diminishing. A galaxy of hundreds of billions of stars, reduced to a footnote in a universe of 2 trillion galaxies, itself nested inside a cluster, inside a supercluster, inside a cosmic web that stretches to the limits of what light can ever tell us. The numbers suggest insignificance by almost any measure. But the map is not the whole story. The map describes what is there. It does not describe what happens within what is there. In this single modest late-arriving spiral galaxy, in one unremarkable arm, around one ordinary star, on one small rocky planet, something emerged that could look at the map and ask what it means. That is not a small thing. Webb's infrared mirrors, floating silently in space at temperatures colder than anything in our solar system, are collecting light from the earliest chapters of cosmic history and sending it back to the planet where the mirrors were designed and built and launched. The universe is photographing itself through instruments we made. The Milky Way is small. The Milky Way is young by cosmic standards. The Milky Way is unremarkable in its position, its mass, its structure, and its future. All of that is confirmed. And yet the Milky Way is the only place in the observable universe that we know for certain has looked back. Begin with one image. A single photograph taken by James Webb. A patch of sky, small enough to cover with a grain of sand held at arm's length. Inside that image, thousands of galaxies, each one containing hundreds of billions of stars, each one a complete, independent island of light, built over billions of years of gravity and gas and time. Look at that image long enough, and something shifts. The numbers stop being numbers and start being something closer to a feeling. Not fear exactly, not awe exactly. Something that sits between those two and has no precise name. This is what Webb has given us, not just data, not just revised estimates of galaxy counts or refined measurements of cosmic expansion, a new felt sense of scale, of where we are, of how old the universe was before our galaxy existed, of how small our local neighborhood is inside the structures that contain it, of how much of what exists is forever beyond our reach, accelerating away into silence. Everything Webb has confirmed about our galaxy's scale is humbling in the most literal sense. The word comes from the Latin for ground, for earth, for low. To be humbled is to be brought down to a truer level, to see yourself as you actually are, relative to what surrounds you. The Milky Way is genuinely small. Not small in an emotional sense, not small as a way of speaking. Small by measurement. Our galaxy is 100,000 light-years across. Some single galaxies are 60 times that size. Our cluster contains 50 galaxies. Some clusters contain thousands. Our supercluster spans 500 million light-years. The observable universe spans 93 billion light-years. At every level of the map, we are a minor entry. But here is what the map does not show. The map is built entirely from information collected by one species on one planet orbiting one star in one galaxy over a few centuries of increasingly sophisticated observation. The entire history of human astronomy, from Galileo's first telescopic observations to Webb's deepest infrared images, represents an extraordinarily brief window of attention directed at a cosmos that has been developing for 13.8 billion years. Webb itself is a product of that attention. A $6 billion instrument, assembled from components made in dozens of countries, launched on a precise trajectory to a gravitationally stable point in space, unfolded in one of the most complex deployment sequences ever attempted, now returning images that no human eye has directly seen because they arrive as data, translated into light by computers. The Milky Way may be small, but it contains something the map has found nowhere else: the capacity to build mirrors and point them at the dark. The journey Webb has started is not finished. Every new observation cycle produces findings that revise the picture. The impossible galaxies will be studied further. The Hubble tension will either be resolved or will force deeper changes to our understanding. The dark matter halos around galaxies, including ours, will be mapped in greater detail. The zone of avoidance will become more transparent. The timeline of the universe will be refined. Every answer Webb provides opens several new questions. That is not a failure of science. It is the signature of science working at the edge of what is known. We are small. We arrived late. We live in a quiet corner of an unremarkable cluster, in a modest supercluster, in one filament of a cosmic web, too vast to fully comprehend. And we built a telescope to look at all of it anyway. That might be the most remarkable thing in any image Webb has ever returned.